Good morning, fellow plebs, fellow maxis, fellow JPEG aficionados, and last but not least, all the millions of people watching from home on their televisions, of course. So by means of introduction, I'm Derek. I work at WalletConnect, and I like wallets. I like to connect wallets, but I also want to get to know you a bit, so please raise your hands if you have a desktop, Chrome, something browser extension wallet. Okay, that's very few of you. Who has a hot wallet on their phone? And no worries, like I don't think this is recorded, so you're not gonna get kidnapped or anything. So yeah, who has a hot wallet on their phone? Who has more than one hot wallet on their phone? Who owns a hardware wallet? Who has like an exotic wallet, like a smart TV wallet? Who has a wallet in their fridge or a smart toaster or something? Okay, so maybe in a couple of years, your AI toaster is gonna hate you because you don't pay it. Thank you. All right, so today we're gonna talk about decentralization, but in some other shape or form. Like, we're going to talk about how you can decentralize a more orthodox service, a more orthodox Web2 type service. So before we kick it off, let's get into what's WalletConnect. Most of you are probably somewhat familiar with WalletConnect. The open source project was started about 5 years ago. The motivation was, at the time, we mainly had dapps on desktop, and we didn't really have remote wallets or hot wallets. And then hot wallets started, but there was still no good way to connect them. So basically, WalletConnect started to connect desktop dapps, browser dapps to hot wallets. But this has changed. Like even this basic use case that we started with has changed. Nowadays, you have wallets in many types of devices. So hot wallets, obviously, hardware wallets, and in Unity, Unreal, in many different places, there's no wallets. And the same is happening for dapps, obviously. We're not going to bring 1 billion people online on desktop, but if we bring 1 billion people, they're going to be on mobile devices and other types of devices. And we have SDKs for all of these platforms. And I think we can expect this mobile revolution, mobile first, that happened many years ago, to also at some point happen in crypto, and we are building the infrastructure for that. And so what's the motivation to decentralize WalletConnect in the first place? I mean, for most people here in the room, that's probably obvious. The crypto ethos mandates this supposedly, but just to bring it back to reality, like other similar messaging services to WalletConnect, let's say email, are somewhat decentralized, but the real incarnation of email is that you choose a provider like Gmail, and if you would want to, like that's decentralized, I can hypothetically move my email to another provider, but it's actually pretty hard. Like I need to update my DNS, and then I need to move my data, and in reality it's like not a really smooth solution. So we want to do better than that and provide end users the option of like obvious things like redundancy, availability. If one WalletConnect node goes down, you can just use another one. Your data is distributed everywhere, and like censorship resistance. And why is WalletConnect maybe a bit different compared from blockchains, for instance? So we have different latency and throughput requirements, and also some requirements on consensus that blockchains have, we don't have. And also the systems we compare ourselves with, like email or WhatsApp, are very cheap, which blockchains aren't necessarily, and also they have way higher throughput than blockchains. So when you look around of what other types of systems solve these solutions while meeting those requirements, there's not much around. Obviously blockchains too expensive, a level lower, libp2p, Waku, also too slow, too expensive to like solve and meet all the throughput requirements, latency requirements, and then traditional databases aren't decentralized enough. So let's take a look at the current high-level architecture. So basically, you have a wallet or a dApp, and that connects through a load balancer to a set of services. So let's say it's WalletConnect chat. One end user is connected to Singapore, another one might be in the US, and so it's different load balancers, and then you're connected to different nodes. They send your messages back and forth via HTTP, and the end user devices are connected via WebSockets, so you have a bidirectional channel. And these things you can sort of decentralize, not so hard. But then in our scenario, we have a routing table, which is it's basically a hash map that says which end user device is connected to which node and whether it's online, basically, such that if both parties are online, we can just send the message directly. But if one of the parties is offline, which is very common in chat, but also in our signed use case when you sign messages and connect the wallet, then the message goes into what we call the mailbox. So next time the client comes online, it just picks up the messages and that it missed, and then they are deleted. All of this obviously is end-to-end encrypted, so we can't see any of the contents of whatever data is being passed through the system. And yeah, so there's nothing off the shelf available. So what we came up with is what we call Nibelung, and all the Wagner aficionados of you are going to be very excited. So we draw some inspiration from the Ring of Nibelung. Obviously, Wagner's big epic from the 19th century. It has its roots in the 13th century when Nibelung was just a poem. And then the German Romantic movement in the 18th century made it popular, and then it became very famous in the 19th century with Wagner. So on a high level, the story is about a ring, and we'll get to that in a second with the architecture design. And in Wagner's, or in the poem, the ring is about whoever owns the ring has world domination or controls world domination. We are not delusional that we think anybody in this case will have world domination, but in the story, the power of the ring obviously motivates and is a catalyst for a scramble of both good and evil actors to get possession of this ring, and that's the interesting story that reverberates into pop culture even today. And I think what's kind of interesting about the story is the Romanticist movement in Germany obviously made this very popular in the 18th century, and Romanticism was a rebellion against the Enlightenment, which was rational. And I think that's kind of an interesting analogy for crypto and for what we're doing here, because in the Enlightenment, you would be very rational, and this is somewhat irrational, because why are we decentralizing this in the first place? Works just fine. So, but obviously, like our ethos, like drives us to do something maybe irrational and decentralize this. So that's why it's sort of rooted in Romanticism. On a architectural layer, this is Cassandra inspired, and Cassandra uses an idea which is called consistent hashing. So basically you have a hash ring, and I'll explain this. And the idea is any of the nodes of the Cassandra database or of any consistent hashing database, Cassandra didn't invent this model. Many other databases use this consistent hashing model. But the general idea is that it's decentralized by design. There's a virtual ring, let's say, that goes from 0 to 10,000, and then it restarts. And every node has an ID, and that ID is hashed to a number that's placed on a ring. So let's take node A with ID something that hashes to, let's say, the number 2000, and another node that hashes to 1000. And now, usually you have a counter or clockwise scheme in this ring. Let's say we have a clockwise scheme, then the node at point 2000 would be, with two nodes, one at 2000, one at 1000, the node at 2000 would be in charge of all the keys and all the data from 2000 to 1000. So let's say I want to read from this database, then I get a key, so it's a KV, a key value store. I get a key, I hash it also to some number, let's say it falls at 1500, so now I know I need to ask node at place 2000 for this value. Same when I write. I also hash it and I know which node I can ask. So there's a couple more challenges here, like what happens when a node comes online or offline. And when a node comes online, it gets an ID, it hashes to the ring, and then it can know, let's say it hashes itself to 1500. Now it knows that it can ask node at 2000 for all the keys from 1500. At some point, the node at 2000 is going to shed the keys from 1500 to 2000. And then there's a similar scheme going on when the node goes offline. I hope that roughly makes sense. And so that's the concept. And because there's this ring, it's decentralized by design. If you take a database like Cassandra, they actually don't care about decentralization. They solve different design goals, such as nodes coming online and offline in a good and performant way. And Cassandra is not decentralized the way it's used, because there's an orchestrator node, and obviously an application that at the end of the day then calls this orchestrator node. In our case, we don't have an orchestrator node. Every node is the WalletConnect application itself and has all the logic, the WebSocket logic, etc., that you saw on the previous slide. And that's why we are fully decentralized, and you can connect to any of these nodes. So instead of just the database package being on the ring, like the entire application sort of is on the ring. And to let the other nodes know whether they're online, we use a popular library called libp2p, probably very popular in this room. Ethereum also and many other blockchains also use libp2p for gossip, basically to broadcast in a decentralized fashion which nodes are online, which nodes are going offline. And we use a popular database called RocksDB for storage. It's a Facebook technology. Cassandra itself uses RocksDB, has many features, Bloom filters, and LSM trees for performance storage, so it's state-of-the-art and database. We also made some contributions to it at WalletConnect. And we have some fancy things to even further push the state-of-the-art of, like Cassandra. Cassandra, for instance, uses regional quorums in a data center. We're going to probably push the envelope a bit in the state-of-the-art of databases if we use a latency-based quorum. Like, to my knowledge, nobody has done that before, and we would provide better cross-region latency. So what are the milestones here? So what we're building right now is a permissioned decentralized database. It's not a permissionless database yet, so you need to get access from WalletConnect to be able to run the system, because we need to trust actors that they're not malicious. But we want to remove this, obviously, and allow anybody out there to run a node. So this year we are battle testing this network, what you just saw, and then we're currently designing how we're going to make this permissionless with a bunch of partners. You're also more than welcome, if you're interested in this, to reach out and take a look at the current design doc of how we're going to make this permissionless. It has some novel requirements and problems to make this permissionless. So, for instance, in blockchains, you have a certain set of things that you need to have consensus on. But in our case, it's different. Like, we don't have to have consensus on all the data that pass through the system, but probably we only have to have consensus on which messages were actually delivered. And we need to know that, because probably we won't be able to just cryptographically secure the system. We will probably have to have an incentive layer. And in order to have an incentive layer, we need to have the consensus and probably reward participants. So the question is, what do we reward people on? How do we find, or how do we penalize bad actors? Some ideas, how do we even detect bad actors? Some ideas are snitch nodes. I think those are common ideas. And how do we design this to be in line with the fallbacks and the drawbacks of the consistent hashing approach, such as the consistent hashing approach other than other technologies like Kademlia, which are also, like IPFS uses Kademlia, and which is built for nodes coming on and offline all the time very quick. In our consistent hashing approach, we can't do that. We get benefits for that, but we can't do it. So we probably need to have some staking slashing layer or other ideas in order to prevent nodes from doing this. And yeah, that's it. Thank you. Again, want to say, if you're interested in becoming a partner, running a node, then reach out. Or if you're interested in reading the design docs for the permissionless network, also reach out. And we'd love to hear your feedback. Do we have time for Q&A? Or?
If anyone has a question, feel free to ask Derek while you have his time and his attention.
Also ask anything about German Romanticism movement. In case you didn't get it, I enjoyed talking about that. Well, awesome then.
How compute heavy are gonna be the nodes? Like, what's the size of the node you're gonna target to?
So the question was, what's the size of the node? So there's different parameters that we're taking into account. So one thing is we want to scale CPU memory independent of scaling storage. So what is the storage size? And like basically how much data can a node hold, and what are the CPU requirements? And we don't really know yet. So currently the centralized system that drives all of the current WalletConnect traffic, the CPU and memory requirements of the actual nodes is very low, and but the requirements on the data storage are a bit higher. So, I mean, we're shooting for very little nodes, at least in terms of CPU memory, and maybe a bit more in terms of data. But how exactly it's going to work, we don't know yet. And for the permission network, where we're going to control this and we're going to mandate certain size of nodes, we also don't know yet. Awesome. Thank you.